Hello everyone, my name is Robin. I'm part of the abstract team. So I'm not actually part of CosmWasm or like the Confio team. If you're looking for someone from a Confio team, you can ask for Simon. And everyone here knows Simon, so they will try to point you in the right direction. But I am a big fanatic of CosmWasm, and I'm gonna try to introduce you to this technology, why it's such a fun to work with, and also some of the technology that we built on top of it. So from a high level, this workshop is going to be an introduction to CosmWasm. So from the basics, what is it, how does it work, what are some of the important concepts that you need to have in order to start writing your first CosmWasm smart contract. Then I'm going to go through some code. So we're going to add a little bit of functionality to a counter contract. And I'm going to show you how to do that in the code, where you need to change the API, how you can manage state, those kind of things, as well as testing your application and deploying it using a tool that that's called CW Orchestrator that we developed and that people and ourselves really love. And then I'm going to jump into some more complex application logic related to IBC using our framework. So that's for the people who already know CosmWasm and who want to start hacking with IBC specifically, and who don't want to go through the hassle of setting up a channel, of creating their own packets, data, and like all that stuff, running your own relay. You don't need to do that. We have that set up for you. If you use our framework, you can start hacking on IBC right now. So without further ado, I'll just jump into this presentation. Sweet. So who built CosmWasm? Just some background. Confio, it's a team from Berlin. They're currently maintaining CosmWasm. And as I said, I'm from Abstract, co-founder. Co-founder is right there. We have a small team, all of which are very passionate about this smart contract framework. So, and as some background, Tendermint and Cosmos SDK was created in 2014. Then during a hackathon in 2018, someone had the brilliant idea of adding smart contracts to Cosmos through a technology called WASM, which I will delve into later. They launched it in 2019. Then Terra adopted the technology, and as you all know, Terra really went insane. A lot of development came into CosmWasm, really made it quite a big technology in the space. Then Terra died, but luckily people stuck around, people love the technology, and right now we're on version 2.0 or like 2.3, I think. So it's really been solidified over the years, and there's a lot more tooling available now compared to when this first got some adoption. Why CosmWasm? So it's a lot safer than Solidity. There's no re-entry risk. And I always describe CosmWasm as kind of a second generation smart contract framework, because there were a lot of lessons that were learned from EVM, from Solidity, that were kind of mitigated in the design of this smart contract framework. It's also very cheap to execute, so you can do very complex logic. You will see contracts that exceed multiple megabytes, and it just shows how complex you can make your applications. The WASM and Rust ecosystem, of course, is amazing because you can reuse all of the crates that are already being used in production systems right now. You can just import them, use them as dependencies, plug them into your smart contracts, and get going. Rust is also a great language for cryptography, which is, of course, an important part of what we do in the space. And it's a lot of fun to work with. So, win-win. And a lot of chains use CosmWasm. So, to give you an overview of like the tech stack of CosmWasm, we have the Cosmos SDK, which is the blockchain, right? It's a modular blockchain. You can have different modules on that blockchain to kind of compartmentalize the functionality. And one of those modules that was developed is the XWasm module. And this WASM module contains a virtual machine, right? And the contract is compiled to WASM, and WASM stands for WebAssembly. So it's like bytecode that we can't really read, but we can easily compile it into whatever bytecode is needed to run on the actual machine. So it's platform agnostic. We can use this WASM bytecode, plug it into this virtual machine that is running on the validator, and then run the contracts there. So something that's really important is that this bytecode or this program is deterministic, right? Everyone who executes this WASM bytecode needs to come to the same conclusions, otherwise we cannot have consensus. But generally this is not something you have to worry about. Most libraries will work, except if you try to do a network request, for example, that will not be possible. And they're written using CosmWasm STD, which is a library that Confio developed. Now into the anatomy of a smart contract. So you can describe a smart contract as its API, right? So the kind of messages you can send to it, as well as its state. And the state is managed internally. So the entry points, i.e. the API, are JSON encoded endpoints. So you define a JSON message, you send it to the smart contract, and depending on which type of endpoint you hit, there will be different rules. And the state is only mutable by itself. So there is no way for me to change the state of Adair's contract, which also makes sense. So the entry points that are available, the most important ones I've listed here. Instantiate lets you create a new instance of a smart contract. So this is important if you're familiar with EVM and Solidity. Uploading a contract and instantiate a contract are two different things. Okay? You first upload the WASM bytecode, and then you can create as many instances of that contract as you want. And each instance will create an address that is unique to your smart contract, and it will have its own state related to that address, and it will run whatever bytecode that you specified. Executing a smart contract means that it can mutate a state during that process, and querying a smart contract means you can only retrieve state. So there is no way for you to change value when you query state, and querying is free, basically. So it's just an RPC request to a node. For example, this is like an API of a smart contract. For a counter smart contract, we have the instantiate message, which has a count. So this is how you instantiate the count. You say, okay, my count when I instantiate this contract will be 5. Then the execute message are the different methods that your contracts support. So you can increment it. Anyone can call this message. We'll see that in the code. And then the reset is how you reset the contract. So if I'm the owner of the contract, I say like, all right, it's 420, haha, funny. No, none of that funny stuff. I'm going to reset it. Then that's what I call. And query is just to get the count. So if you have a front end, you want to show how many counts your contract got, then you call this and you show the count on your front end. Cool, so that was the API. And now we're going to talk a little bit about state. So state is mainly instantiated during the instantiation. So you, like I showed you earlier, you get the JSON encoded message, then you say, okay, I'm going to save the count. And the state is also JSON encoded right now. So yeah, that's not really that important. But there are some data structures that are created for you, just to make it easy for you. So one of them is item, the other one is map, so you can store items and maps and all those common data structures. So here's another example to just make it clear. You have this state object with a count and an owner. And this CW survey macro, it just ensures that your data structure is serializable and deserializable into the JSON format. So you will see that in almost all of your structures. If you're getting like weird errors saying, oh, you can't serialize a type, missing trait, just add that macro and it will solve all those problems. And then this is a definition of some state. So you have an item, you give it a state type, and then you give the namespace. This is not that important, just make sure that they never conflict with any other items that you create or maps. And then to use it in your actual logic, you can save to state and you can load state. So it's quite basic. Little pause. Are there any questions about what I have just been preaching? Nope. Okay, sweet. I hope I did a good job. So now for the next part of the workshop, if you actually want to get going and started with developing CosmWasm, you should install Rust. Maybe who will actually want to follow this workshop? Can you put your hands up? Like actually code? Okay, sweet. Yeah, do you have Rust installed, guys? Okay, so we're good to go. Can you install a cargo generate? So using the command that's on here, this will allow you to generate the template that I'm about to show you. And just give me a heads up when you install it. And this link is pointing to the abstract SDK CosmWasm template. Most links will point you to the Confio CosmWasm template, but I'll show you what changes we made and also why when I run through this code. Just let me know when you guys are set up. And if you scan the QR code, it will go to the GitHub repo of the template, and in the README you can also see the instructions for how to set it up. Cool. So I'm gonna continue. So what we're gonna do is just kind of go over the basic syntax that you will run into in a CosmWasm contract. And we'll do that by implementing two functions. I will go over this quite quickly, just so that we also have some time to go into the IBC stuff. Oh, this is Simon from Confio, by the way. If you have more deep questions about CosmWasm. But yeah, so let's go into this. So the thing that we're going to implement with the previous counter example is we're going to implement a function that allows anyone to become the admin by buying their way into that position. So we will set a price during the instantiation, and then anyone who wants to pay that price to become the admin can call this buyAdmin function, and if they provided enough funds, then they will become the admin and they will be able to reset the counter. And then we will add a query message which will check for a given address whether they are able to buy the admin privileges, i.e. do they have enough funds to pay for it. Okay, maybe just to show the structure of the repo if you have cloned it. So, as with any Rust project, you have a source directory, you have some tests that we will show, you have your cargo.toml with the most important CosmWasm imports, You will see these throughout, so when you get a little bit curious, just check out the Creates documentation. It's all very well documented. There's a developing.md, which will explain a bit more about how you compile the contract and deploy it. Yeah, and the rest we will actually run through, and the README in the repo is also very extensive, so you can read it when you have your time. Cool, so the first thing we will do, as I said, was to update the instantiate message, right? So we're gonna add a coin. The coin represents a Cosmos SDK coin, and we're gonna add that in the instantiate message to set the price when we create a contract. And we're also gonna add this buy admin function, and notice how it doesn't include any information about the payment, right? We'll see later where that's available, but you don't need to specify it for coin types. And then also this macro, I will explain in the testing why we added it, just the same with this one. So that's the API that we changed. Now in the state we need to do the same. Somehow we need to store the last price at which it was bought, because we only want to accept offers that are higher, explicitly higher than the last price. So we will store that in the same state. And this is, so this is basically what the CWSurday macro contains. It's a bunch of different derives, but you can just replace this with the CWSurday macro. It doesn't really matter. So that's the first step. Step 2 is in our contracts. Okay, so in our contract, we have our instantiate function. So this is the entry point that I was talking about. This is the function that will be called when you instantiate your contract through the blockchain. And that's also indicated by this macro, this entry point macro. That's a part of CosmWasm SCD. And first thing we change is to add the last price in the state. And in the execute message, we now have this new variant, this buy admin, and we call the buy admin function, which is a new function that we create. And yeah, buy admin, to implement it, we're gonna first load the state to load the state, because we need to know what the last price was. So we get the last price. Then we use info.funds. So info.funds contains, let me start this. It's quite easy. Info.funds contains the funds that were sent along with this contract call. So here we can actually check whether the caller is doing a payment, and if so, whether that payment is sufficient. So you see funds and also the sender. And we're also going to use the sender, because if the denomination of the payment is not the same, or the amount is not equivalent or bigger, then we will throw this error. And if it is, then we will continue to update the state item with depths.storage. So depths.storage is where you get to mutatable storage. Specifically on depths mute, we will see that in queries this is just depths, because you can't mutate it. And we will set the owner of the state to info.sender as the person who's paying, and we will set the last price to whatever was paid. For your contract, you will probably also want to add custom error types, so that when the contract errors, you know what's going on, right? It helps you in debugging. So that's where the contract error is used. So in error.rs, you can add new variants in this enum. It uses the this error create. So in our case, we added this invalid payment because we expected more than, and that's the last price, so the expected, but we received whatever we received. So if you try to do this on chain and you don't provide enough funds, then this will throw an error and it will tell you, hey, you should provide 100 Osmo, but you provided 10 Osmo. Oh, that's quite useful. So that's number 2. Number 3 is a query, right? So this is an important one as well. If we can do this, yes. So in the query message, we added this can by query where we provide the address. An important thing to know is that when you provide an address, when you expect to receive an address from someone in a smart contract, you should always receive it as a string and verify it inside of your smart contract, because you can't trust the input of random users, right? You need to verify that this is a valid address before you do anything with it. So that's what we're gonna do. In the contract, we're gonna match on this query message. We're gonna take the address provided to our can by function. And in our can by, we're gonna use deps. So now that this is like deps mute, but the only difference is we can't mute its state with this. We can only read. And deps has an API. And the API is quite useful because it also contains different cryptographic functions. So these are a lot cheaper to execute through the API compared to importing a cryptographic library and doing the computations in your smart contract. And one of the functions that it has is address validate. An address validate will take a string and it will turn it into an address. And the address is now validated, and if it doesn't succeed, it will throw an error and you will know that it's not a valid address. So then we'll load the state. We will get the state, and then we want to know whether this address has enough funds to buy the admin rights at the current price. And to do that, we can use this querier. So a querier is like it's just a way to query the chain, and it exposes a lot of Cosmos SDK specific queries that you can easily use in your smart contract. So, for example, validators or like delegations, all that kind of stuff. Also, queries to other smart contracts can be done with this. And one of the queries that is in here is query balance. So we're gonna query the balance of the address that was provided, that we validated, and we're gonna check the balance for the specific denom of our last price. And then we're gonna assert that their balance is higher than the last price, because in that case they can buy it, and if not, then it will be false, and then we return that in a response, and we have the query implemented. Any more questions on this? Am I going too fast? Am I going too slow? It's good? Okay, then we can jump into testing, because that's the most thrilling part about writing smart contracts. It's a really important part. So in CosmWasm, there are really two kinds of tests. You can do unit tests or integration tests. Unit tests are supposed to test your functions in a quite isolated manner. So you can make sure that, for example, you do an assertion on some state, or after you do a function, the state contains what you expect it to contain. And to do this, CosmWasm has a bunch of helpers. If you go to CosmWasm testing, mock, in there you will find a bunch of helpers that create mock types for you that you can use to play with the state and to do things. So for example, this mock dependencies will create dependencies objects that we saw in the functions earlier. The info, message info will do the same to get the message info. And here we will instantiate, so we will try to test the instantiation. We create an instantiate. We call the instantiate function that I showed earlier. So it's this one. Then we create a new admin. We attach some coins to the call. We create the execute message, and here we try to actually buy the admin with our 1 Earth payment. But if you look in the instantiate message, we set the price to 1,000 Earth. So it's not enough. and we will match that on the result. So our result will return our error, which is contract error, invalid payment. We expected 1,000, but we received 1. Sorry, you're not gonna buy that. Now in the second one, we actually provide 1,001, which should be enough, and we can assert that it is okay. So now we should be the admin, and we can try it by doing a reset of the count using the same sender. So this info is the same as before, and it actually succeeds. So we became the new admin, and then we can get the count and assert that it was 5 because we reset it to 5. So this is already kind of a pretty long unit test. Most of the time they will be shorter, but just to give you an idea.
Can you close the terminal?
Yeah. Nice. And then the other way to test things is more for, if you're interacting with multiple contracts, is with CW Orchestrator mocks. So these are integration tests, and you will find this file in tests counter.rs. And what we will do here is we will create kind of a mock instance of a blockchain, let's say, that is purely in memory. And we will create a new address. We will deploy our counters through an interface. So this is interface .rs. This is some CW Orchestrator specific code. I won't bore you too much with this. If you're interested about how this works or how to work with it, you can go to our documentation. So, just show you quickly. CW Orchestrator, it's basically a tool that lets you test your smart contract, deploy it, interact with it very easily. And it should just make your life easier when you're trying to test things. Otherwise, things get very verbose. So for example, this deploy function that we created, we implemented it on the interface, and you can see that we create this object, we call upload on it, we instantiate it with the instantiate message, and then we return it. So this syntax of just like uploading and instantiating is something that CW Orchestrator enables. And then within the test itself, we can set balances, we can call functions on the contract. So the scan by function is something that we implemented, but this function itself, we didn't write it. It was generated through the macros that we added. So it's just really nice to not have to write too much code for your testing and just be able to start testing. Okay, and I think that kind of covers the testing part of it. You can go a lot deeper with it. There are a lot of caveats within Cosmos, but just to get started, that's about all the things you need to know. So then to actually deploy the contract, we're gonna use an optimizer. So the reason why we use optimizers is so that the builds are reproducible. That's really important if you make your source code open source, and you want people to actually be able to verify whether what they are running is the thing that they're looking at on their screens, on their GitHubs. It needs to be reproducible, and that's why we use an optimizer. To use the optimizer, you can just do /optimizer.sh. You need to have Docker running. Sweet, and then it will compile the contract, and at the end of compiling it, it will put the artifact in this artifacts folder. Shouldn't take too long. So now it's optimizing bytecode. Sweet. So now we have that .wasm. And the reason why reproducibility is so important is because once we upload this wasm bytecode, no one really knows what the source code is. If you try to look at what this file contains, it's just a bunch of binary data. It's not human readable. You can't interpret it. So it's different from how Solidity works. Not really, but cool. And then to deploy it, so you want to actually run it. You want to get it on a test net, on a mainnet, on a local blockchain. You can use deploy.rs, which is a script. So we use .env to load environment variables. So I have a .env file here that I'm not gonna show because I'm not sure which mnemonic it contains. But just know that when you copy the templates, when you do the generate, cargo generate, you will have this .env file. It will ask you for a mnemonic. You just specify the mnemonic for whichever chain you want to use. In our case, we're going to be using Pion1, which is neutron testnet. Env logger is also important, so we can get logs. Within .env, you can also set the level of logging, so you can debug info, etc., etc. We're going to build a daemon. So this is C-level orchestrator code. We're going to do the same function that we did earlier within our tests. So this is a really cool feature about orchestrator. We wrote this deploy function, but we can use it inside of our tests, but we can also use it inside of with an actual daemon. So we don't care about what the execution environment of the CosmWasm contract is. We just write a function for any generic CosmWasm execution environment, and then it's available and you can run it anywhere. And we love this. And then we're gonna increment the counter, we're gonna get the count, and we're gonna assert it. So let me try to run this live demo. Sweet, so it's uploading, right? Contract viable counter uploading, awaiting transaction inclusion. We got the transaction hash, we got the code ID, so now it's instantiating. It's instantiated, we got the address, and now we're incrementing it. And we incremented it, and our get count and assertion succeeded because we didn't get an error. So it worked. Nice. This is as far as it goes for the viable counter. Are there any questions about the code specifically that I went over? Okay, so some of the things that I didn't cover are executing other contracts and querying other contracts, migrations, replies, calling into Cosmos modules or custom Cosmos modules, IBC I haven't covered yet, custom key types, CosmWasm standards, like all of these things. If you're interested in them, if you think, oh, I think I might need this feature, I don't know how it works, come talk to me or my co-founder. Will happily get you set up with whatever knowledge you need. Cool, so this is all that I'm going to cover for like the basic CosmWasm stuff. Who's here for the more advanced IBC logic? Okay, cool. So I'm going to jump into that next. Yes. So the next thing I'm going to cover is module-to-module IBC on the abstract framework. So a little bit of background. I think I might have some slides on this. This was from our workshop during the Hackmos earlier this year in Berlin. Cool, yes. So what's important to know about abstract is that the framework works with accounts, abstract accounts, and they're smart contract wallets that can have applications installed with them. And then these applications can be modular. So in the case of IBC applications, what we're gonna do is we're gonna create an account, and we're gonna install an IBC client on top of that account. And this IBC client is responsible for handling all the IBC-related logic that any application or the account itself will want to do. So it will facilitate communicating with other instances of abstract on any CosmWasm chain. So we deploy abstract on as many chains as we can, and we connect them, and we make sure that they are relayed, so you don't have to reach out to validators and try to set up a channel and get the pings in the middle of the night that the channel is down and all that stuff. So these interchain abstract accounts, they can be, so that's an account, right, on Juno, and they can create other accounts on different chains. So you can say, oh, I want an interchain account on Terra for my Juno account. Oh, but then I want another one on Archway from the Terra one, and then I want another one, right? So you can just create a web of interchain accounts if you want. I wouldn't necessarily recommend doing this, but it's possible. And then on top of this, we created something that we call interchain module communication, and it allows you to specify messages to a specific chain, to a specific module, with a specific message and with some callback information. So the example that we have is the IBC mail. So the idea here is that we locally submit a message, and that gets sent over IBC to a different account. So locally, we can just do this by creating a smart contract, installing it on 2 accounts, and then those two smart contracts just communicate to each other by sending messages. So I say, send this message to Adair. Our infrastructure figures out what the account is of Adair, and then figures out what the IBC app is that Adair has installed, and it will then send a message to that app. If we want to do it over IBC, we can create a server. I'm not going to go into the architecture too much, but just know that we want servers to be able to talk to each other. And we do that with module-to-module IBC. So I'm just going to show you an example of an application that we have, and we call it a ping pong app. So ping pong app is very simple. It will be instantiated on 2 different chains, and it will send a message to an instance of itself on another chain, and it will say ping. And then the app on that chain, ping pong app on that chain, will receive the message, and it will say pong. Right? So you get the point. Let me just grab some water. Okay, so this is a lot of kind of boilerplate. You don't have to construct this yourself. You can just go to our templates repository, and you can follow the README, very similar to the template that we used previously. This one will set up an abstract app if you tell it to, and it will ask you if you want to include IBC-specific functionality. In your case, you will want to do that. So yeah, just follow this, and you should be able to get set up. And then you will have something similar to what I'm about to show you. So here we define an app. So this is an app that will be installed on an account. And we provide an application ID, in our case, abstract ping pong, and an app version. So abstract is a namespace. So we own the abstract namespace. Your project will need to claim a namespace as well, which is quite easy. I will show you how that's done. And then the specific ID of the app, in our case, is ping pong. This is important because we will use this identification to ensure that the messages we receive on the receiving end actually come from the instance that we wanted to come from. We don't want to receive messages from ping, right? That would be weird. And this is like a constructor for it. The most important thing here is that you provide the IBC client as a dependency. So when this app is installed, our infrastructure will make sure that you have this IBC client installed on your account as well. Go ahead.
Yeah, good question. So to make IBC call from contract to contract, you need to set up a dedicated channel, right, for those contracts?
We set up the channel for you.
Ah, nice.
So you don't have to do that anymore.
So it means that you have like a backend running with Hermes that is...
Yeah, so the question is, do you have to set up a channel yourself to work with IBC? The answer is no. We have set up a channel for you, and we have connections with the relayers. They are actively relaying the channel. We're making sure that those channels work, so that you can just focus on building your application, calling the IBC packets, and we will handle the relaying. If it doesn't work, reach out to us, and we will handle it.
So you create channels on demand?
Yeah, no, so in the backend, we actually use Polytone. So Polytone is a CosmWasm interchain account implementation, and we kind of use it just to do the transportation of our packets, because it's audited. So, you know, getting an IBC implementation audited is quite expensive. So they've already done it. It's quite a nice API. It has some minor issues, but in general, it's very nice. So we just use that as kind of the backend, which is also nice because DAO actually uses Polytone as well. So we can just reuse the connections that DAO is using because they also have interchain connections. Yes, go ahead.
So, as it's using a different channel, like using Polytone with the backend, is the IBC canonical with what, like let's say I want to do IBC transfer with a login account and with an admin account, will that be like similar?
Yeah. So the question is, if you transport tokens using our framework, will those be the same tokens as what other people are using? And the answer is yes, because we don't define any token like channels, right? We reuse the ones that already exist. So if you use our infrastructure to send tokens, we will just send them through the canonical channel, and they will be the same tokens on the other side. So the channel that we use is purely for message passing. It's purely for sending executions. It's not for sending tokens. Okay, so the client is for executing actions. Receive module IBC is a function that will receive the IBC packet. So let's just click into that one. When we receive this message, it's a binary message because any IBC module can call this endpoint, right? So the first thing we need to do is we need to make sure that whatever is calling us is a ping pong app, because we just want ping pong apps communicating. So to do that, we get the current module information from the module. So this is something that is abstract specific. Whenever you're working with abstract, you will have this this module type available, and this represents your application. And we can get some information about that application. So we can say .module info, this module info, and this module info will be abstract ping pong app. And the source module is provided by the infrastructure. So when this is executed, we know where the call came from. So that's chain, and we would know the module. So we know which application of that chain is calling us. And then we can just assert that they're the same. We say the source module and this module should be the same. If not, then we need to throw an error. Now that we know they're the same, we also know what kind of message that they're sending. So we can decode the message from JSON, deserialize it into our ping pong IBC message, and then we can ensure that they ping me. Because yeah, on the receiving end, you should always receive a ping. And then we can return with the response. And then there's just some logic that like makes sure that it doesn't keep going indefinitely. So we only send back a pong if the block height is in even number. And otherwise we update some state. Cool, so now I got an IBC message and I don't really do anything. I'm not calling back pong. The pong is going to happen in the callback. So that's maybe a little bit unintuitive. But we'll go to the sending part first, because how did I initially send that message in the first place? We'll do that in the Sping Pong app, in the Sping Pong execute. So here we select the opponent chain. So the opponent chain is a chain to which we will want to send this message. And it's a truncated chain ID, i.e., it's Cosmos Hub, Juno, it's just the name of the chain. And then we can get the IBC client. So from this app object, we use the abstract SDK. The abstract SDK contains a lot of different APIs. And these APIs just enable you to do transfers. They enable you to call into our IBC client. And also, if you develop an app and you want other developers to be able to call that app, you can create your own API, and they can import it, and they can use it just like we do. So it's very modular and composable. So with this IBC client, we can call a module IBC action. We can say we want to send this to the opponent chain that we specified. The target module is self, right? It's our abstract ping pong app, but on a different chain. And the message that we want to send is a ping. And then the callback is going to be called when the acknowledgement is received on the current chain. So we send an IBC message, the IBC is processed, the IBC protocol will send an acknowledgement, and normally when we receive that acknowledgement, nothing will happen. But with this, we can say when we receive that acknowledgement, let me know, because there might be something in there, or there might be some state that I need to update. And also, if the action on the remote chain failed, if that's an error, you will still receive the callback, and you can check whether it actually succeeded or not. And if it failed, you can roll back state. So this is all really important stuff when you're working with IBC, because it's asynchronous. And then we return our response. So that's just a regular response. And then in the callback, callback is also specified on the contract, right? So we do with dependencies, with module IBC, with callback, and these functions will be type checked, so don't be afraid of making mistakes in the attributes. We can deserialize the callback. This callback will be ensured that this is being called from the infrastructure, so you don't get random callbacks from random contracts. You can deconstruct the original message that you sent, so you can get the opponent chain, you can do some formatting on it, like do some logic, but it's not really important what's going on here. It's just you can get callbacks, you can execute stuff on those callbacks, etc. So that's kind of a small implementation. To see this application, you can go to the abstract monorepo. Abstract SDK on GitHub, abstracts, modules, contracts, apps, ping pong. Right, so this is it, and there's a little bit of an explanation of what it does as well. Okay, that's the logic. I can also show how we test it, because we have some testing infrastructure for application logics, for IBC applications. So we're using Serial Orchestrator extensively. There's documentation on the interchain tooling that we provide as well. So this struct, or ping pong struct, is gonna encapsulate the whole thing. It's gonna contain an abstract client, which represents the deployment of abstracts on Juno. It's gonna contain one for like Stargaze, quote unquote, right? These are all mock implementations. It's gonna contain the application itself, so the instance of that application on the chain, and the remote account. So that's the remote account that we created, where we also installed the ping pong app on, and these two ping pong apps are gonna communicate. And then we're gonna store just the environment, so like the chains, apps, it's just all the state that we have, which is this IBC environment. To set this up, we can use the mock back32 interchain environment that we expose in CRB Orchestrator. We create a Juno chain with Juno token, a Stargaze with Stargaze token. So here we can specify n number of chains, and these will be mock chains in your memory. And then we can create an abstract interchain client. So this is specifically to, when you create this, it will deploy abstract to all of the chains that you specified. It will connect those abstract instances, so they're all interconnected. And then you don't have to worry about any of the IBC stuff, right? It's all set up for you. And you can get the clients by calling the client with the chain ID. So you have the different clients. Then we're gonna get the namespace from our app ID. So this will get the abstract namespace. And then we're gonna create a publisher builder. So publisher is an account that will claim a namespace and then will register this application on the infrastructure. And you can do that, so with the publisher, publish app, you provide the type, this app interface, which is the CW orchestrated interface that was created, and it will do all the inference, so it will just say, claim the namespace and publish the application so that everyone knows that this contract is the ping pong app. And then we install it. So we install this app interface with dependencies. So this will ensure that it also installs the IBC client, because we added that as a dependency. And then on Stargaze, we will also publish the app. And then we will, what is this app? We will get the account of the app that we installed, of the ping pong app, and then we will create a remote account builder for that. We will create a remote account on Stargaze for the current Juno account, and we will, on that account, we will install the same application, app interface, and we will build that, and then we get the remote account with the ping pong app installed, and then that returns our ping pong instance. So it is quite complex already, right? It's just a ping pong app, but yeah, there's some setup that needs to be done. But once that's set up, the tests are actually quite easy, right? So we do the setup, we got our ping pong, we got our application. So in this case, we just want to successfully install. We got the game status, which is like one of the queries that are exposed in our app. And we assert that it's 0, and then we kind of do the same for the remote application. We have some more tests here that will actually do the packet sending. Yeah, if you're building our application, you can look at these tests and kind of figure out what the logic is that you need to call. So yeah, I think that's about it. Are there any questions?
Where can we find docs?
Yes, you can find the documentation on docs.abstract.money. So docs.abstract.money. For the orchestrator, it's orchestrator.abstract.money. Yeah, and again, this ping pong app abstract monorepo, abstract modules, contracts, apps, ping pong. Go ahead.
Has to set up support some sidecar processes, can you do some other processes?
Yes, so the tests that I showed you were purely in memory, but we applied the same concept as we did with the CosmWasm execution environment. So remember how we had this deploy function where we could insert the mock, but we could also insert the daemon, like an actual chain that's running, and use gRPC. We did the same. So instead of, let me actually see, I think we have an example of this. 1 second. Okay, so we actually support Starship. Are you familiar with Starship? Cool, so you can spin up Starship, you can configure Starship, spin it up, you have like whatever networks, the relayer is all handled by Starship. In your test, we just connect to Starship, we figure out the networks, which ports to use to communicate to it, etc. And yeah, we basically implement this this interchain environment trait for Starship. So if you look at the setup function, notice how it's generic, right? So this generic, you might not be able to read it, but it's a mock back32 interchain environment. And this mock back32 interchain environment, oh yeah, no, that's a mock. Oof. It's IBC environment, yeah, interchain environment. So basically, yes, you can use Starship and do the same logic with Starship, but that will take longer, right? So in some cases, you might want to call some gRPC messages in the contract, right? You either have to mock those in your mock, or you can spin up a chain and run it on actual binary. Yeah, so depending on your needs, that's how you do it. Cool, okay. Thank you. If you have any more questions, feel free to come by and happy to answer. Right.
What does it do for Adam?
I'll let that speak for itself.
That was super good. Well done.